Nope.
Test, 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 test.
Yeah, we can hear you now.
Oh, thank you. What an embarrassment. I guess let me start over. Um, so I apologize for that. It figured because I don't have Gosha here. So one of the things I was trying to say um, in starting over is the welcome to the May 2020 installment of the FORGE Modeling and Simulation Forum. Um, I am actually running this myself today. Gosha, who normally runs this, or at least does all the IT work behind it, is on vacation this week. So you understand here. So I thank you for bearing with me for my initial technical difficulties. I have no idea why my headset microphone wasn't working. Chris Catisse, I noticed that you're on. I made you the co-host, and I would ask that you can kind of help me manage this a little bit as we go through. Some housekeeping is when you first come on, if you haven't muted your audio, please do. If you have questions, you can type them into the chat box. I won't look at the chat box too much as I go. I'm glad I did when I first started because it'd be a very boring 90 minutes of a meeting or an hour with me just talking to myself. But I will come back to those and go through questions at the end. And so, so instead of not wasting any more time, we'll go from there. Um, so as an outline, the what I want to go over today is there's been a lot of things that have been happening at the site and the team. Things have just been very, very busy. So the first thing I want to do is just give the modeling community an overview of the site status and the schedule, the near-term schedule anyway. I'll also present an update on the modeling activities that we've been doing as a FORGE team itself, the internal team, and also some of our near-term plans, things that are going to be happening here in the near future. Most importantly, what I want to do is give a little bit of an overview, excuse me, of the FORGE solicitation 2020-1. There are a number of projects that were selected for award negotiation that had a significant component of modeling and simulation. So I reached out to a number of those people, a number of those PIs, to ask for just a high-level summary of what they intend to do. And I didn't get a response from everyone, but the people I did get a response from, I will present and go through what they sent back. I didn't edit their slides. I didn't want to go through and take the, I know there's all kind of award negotiations. Um, and I am just going to think I'm going to have to monitor this a little bit here as I go through to keep things clean. If you're not muted, please do. And last, so we'll go through some of those projects, and last we'll have, hopefully a good bit of time for discussion and questions. And so we'll just launch right in from there. So the status and schedule, I'm sure everyone is aware, but I wanted to go through it anyway, is that the first full-size large offset well was completed, drilled and completed, and I would say record time, had very good success with directional drilling, had very good success with rates of penetration, with bits, with downhole mud motors. I mean, there were some challenges here, but I think we can comfortably say that it was like done in record time for large offset hard rock geothermal wells. That drilled nominally at the build anyway of 5 degrees per 100 feet with a kickoff point at just a little bit shy of 6,000 feet measured depth. So you're looking at here on the right, the rig, so drilled down to almost 6,000 feet, and then started building the curve. It went on an azimuth of approximately northeast at 105 degrees, which is nominally in alignment with the principal stress direction, a little bit off of it. The curve landing, so as it came out of the curve, it took it all the way down to about 7,200 feet measured depth, and it ran at a 65-degree inclination. The total depth of the well was just shy of 11,000 feet. I'll show, I think, some of those things here in a schematic. So yeah, as I said earlier, the kickoff was just at about 6,000 feet. Blue dashed line was the plan. The actually a little bit of a curvy line is the actual well trajectory of the well path. Did collect a number of logs here, so we have for different stages and different levels. We have some ultrasonic borehole imagers, formation microimagers, some of your standard logs, and a misspelling by Podgorney on the slide. We are intending to collect more logs in the very near future. getting equilibrated temperatures in this well as well as some others. We did a number or a small number of injection tests at the toe of 16A as well that were completed. So number of areas of core were also collected here. Core was collected in 2 different locations in this well. We're pretty happy with it, and we're ready to get started to do some real work in it. So that's kind of what we're building up to here, with at least not only preparing the site, but also preparing the some of the models. So current and pending infrastructure. So here's air photo looking from nominally the west, or looking to the northwest from the northeast. I apologize. This is all on the FORGE site. So our pilot well, the 5832 that was drilled in 2017, this is the pad for that. So this is, for reference. There's our north arrow. A couple other existing, so in white are things that exist right now. So some seismic monitoring wells exist. Well 16A 7032, that is our large offset well. So this dashed line is the approximate trajectory of that well in the subsurface. It ends right about here. This is in the Magley Wash, essentially a little bit off in the Magley Wash. This well was also just recently drilled. 5632 is a deep seismic monitoring well, drilled to over 9,000 feet measured depth. There is I think I'm going to go. It's shown here in yellow, or some additionally planned wells. So these WU1, WU2, 16B, essentially our production well. This is our plan for our injection well. For a production well would also be planned here on the same pad, and 2 additional testing / seismic monitoring wells are currently planned. So the near-term schedule, and this is what's important here. So and these are taking a little bit of wiggle room here, but nominally in June or July of this year, so just coming up next month or the month after, we'll drill that WU1 here as a deep seismic monitoring well and a testing well for tools and equipment. What's important is going to get this done in July, that way we'll have fairly deep coverage at reservoir depth. So this will go down to 9,500 feet, and we should be able to get very good control based on our seismic detection modeling, between this monitoring well at 9,000. The toe of this hole is nominally about that depth or a little bit shallower. We also have 1,000-foot accelerometer seismic monitoring hole here. We'll do monitoring in the pilot well 5832 as well as this. And there is an outer ring of seismic monitoring plus nodal arrays that will all go in. Important part is this well will be completed and be able to monitor it before we begin doing testing in the toe of 16A. So in August, September of this year, we'll stimulate a portion of the open borehole, the open toe of 16A. And additionally, we're planning on doing 2 case zones. So we'll do some perf, plug and perf, and do some stimulation in different areas in the toe of 16A. We'll have deployed deep geophone strings. We have distributed acoustic sensors, a number of wells in those deep wells. So we should have really good coverage, really good detection. Coming in next spring, nominally we just loosely planned for April of next year right now, is drill the production well, the 16B well, to drill, intersect, and begin to be able to prepare to do flow testing at the site. Late next fall, October of 22, give or take, stimulate 16A and B as necessary and test newly created reservoir. So that's when things really became really important. And as we go further into the testing, March of 2023, drill that second deep well here, which this location is approximate, but drill it in here. And then in April of that year, we can start some long-term circulation tests. So a lot going on, a lot planned for the next 6 to 24 months, give or take, at the site. Very exciting time. Lots going on. Very, very fun. So I want to talk a little bit now about the modeling and simulation that we've been doing and give an update on that as it relates to all that's going on here. But first, I just wanted to introduce the people that are active in the FORGE modeling and simulation team. And I would say active in the team. So the team has changed as the stages of FORGE have evolved. It's grown. We've had some people come, some people go. But I just want to say who's active in it right now. I lead the team still. Alita Finella and Tom Doe at Golder have been working pretty hard in DFN development, stimulation upscale, or I gotta hide my camera display here, I'm sorry. It's covering some of my screen. I'm trying to make it go away. Okay, so back to that. So Alita and Tom at Gold are developing the DFNs, analyzing the logs, doing some stimulation modeling, upscaling of permeability, upscaling of the Frasher networks, etc. Branko Demjanic, Zarisa, Murillo at Itasca. They've been focusing on stimulation modeling, stress analysis, MEQ forecasting. Pengju Jing, Pranay Desai, Alex Gauratrov at the University of Utah, as well as I want to forget to mention John McClellan, my close collaborator, been doing stimulation modeling as well, stress analysis, looking at well completion, different configurations and different well designs. And lastly, I want to mention some of the people, my colleagues here at the INL, Jerry Liu, Chandu, KT, Lynn, David, Hari. We're spreading things out a little bit, is handing off some of the day-to-day modeling that I've been doing to the team at large. So we've been working on earth modeling, a lot of the native state modeling, some stimulation modeling as well, longer term operations, seismic wave propagation, and also some computational fluid dynamic approaches to augment some more standard modeling techniques. There's a number of people here that I could mention also, like Ahmad Ghassemi, who worked with the team a number through parts of phase 2. I would Brian Forbes, who was a former EGI employee who's worked with us and left a number of other former students and postdocs at the University of Utah to participate on the team as well. I won't mention them all, but thanks to everyone. And I think we have a pretty good team here. I'm really happy to work with them. So firstly, as far as what we've been doing now, and I'm just going to go through this in the order of operations that we do. So we've been doing Earth model updates. As I said, we've completed a number of deep wells in the very recent past. That 16A well, 5632, and the others planned. So they've given us a lot more control over things like the fractures, over things like the top of the granite. Earlier, essentially what we're looking at here on the right is this is one of the cross lines from the 3D seismic where the interpreted top of granite was picked. This is a long well, 5832, so that actually comes through right here. At the time, we have a number of deep wells, 3D seismic reflection. It's interpreted to be an exhumed footwall of a rotated basin range fault, and we didn't see any rotation or any offset observed in the basement at or near the FORGE site, especially in regard to the Opal Mound fault or others. But what's important here with the new well control is that these additional wells, they're really giving us a lot greater control on the top of granite interpretation. So what I'm seeing here on the right are some of the control points, either from 3D seismic, from some other methods that we use to build the top of granite surface of that contact. But what you notice here, actually, so what I'm showing here in red is 16A. That's a new well. That's a dot for the new well. Some of these other wells that are newly added to this interpretation. And what's important to notice is actually we were getting some of these top of granite measured in the logs that were significantly higher than what we saw in some of the 3D seismic. So we went through and we integrated all the drilling control data, took a new look at the 3D seismic, magnetotellurics, the nodal seismic velocity modeling that was done by the seismic monitoring team. And we did actually establish a new reference top of granite. What you're seeing here on the right is not the reference top of granite. It's an example of the data that we looked at here to look at it. So we actually reinterpreted a lot of these things. We are still waiting, as far as additional data that's going into the Earth model, things like new temperature logs that we don't have full equivalent temperature logs from those new wells, but those will all get built into there as well. So for right now, the main change we're pushing in for the Earth model update is the new top of granite. It is done. It is in our Leapfrog model, but it is not published yet. So we haven't ported that out and published it to the community just yet, but we will do that shortly. Moving on to the DFN. So the status and the revision of the DFN or discrete fracture networks. We did actually collect very high quality FMI logs in the new well. So what we're showing here, this is the work from Alita Fanilla. And I should have said from the previous slide, it's work from Hari Nupani at the INL. This is Alita Fanilla at Golder's work. But what we're showing here is upper hemisphere plots for fracture poles. This is well 5832. This was our initial pilot well at the site, drilled in 2017. But this is a vertical well. Here's some of the response or the detections and fractures in well 16A. This is below 2,500 meters. This is getting more into the horizontal or the sub-horizontal section of the well. And you see, this is actually a different well 5632 was drilled just to the other side of 16A. So on the map, this is actually the order that we'd find them on the ground, and they're within, hundreds of, within a kilometer of one another, I would say. I'm not sure the exact, but what the important part of taking away here is originally we had identified 3 prominent fracture sets. Alita teased out a 4th one, and so we've updated the DFN to include that, even accounting for some of the potential bias in the well for the directional drilling. And I think I have another slide. And so we put a lot of work to recently is between hydraulic apertures and mechanical apertures. Well, some of the feedback or the information we get from the FMI logs. And so essentially the mechanical apertures from the FMI are generally coming in the range of about 0.1 millimeter, while the hydraulic apertures from the well tests are a couple order of magnitude smaller. We use these things to push through here. I'm not going to explain and go through all these things, but what you're seeing here essentially is some of the aperture sizes and the spacing on this upper hemisphere fracture pole plot. This is from 5832, and you see some of the aperture distribution from some of these different FMI runs. Interesting data. It's all been built in, and we're really happy with that. We haven't pushed those out to the GDR just yet either, but this is all happening within the last, I would say, in the weeks is how fresh off the presses these things are. Important here, some of the highlights of this, the update of the DFN. So here's actually another view of the site. This is being the top of the granite here as well, 16A. You can kind of see it coming through here, deviated through, and these are some of our monitoring wells that we have that are coming down to the reservoir level. What's important here is, we knew exactly where, many fractures intersect 16A. I won't say all, but many. We do actually have a pretty extensive and well-connected, but not very transmissive. We're working on predictions now regarding which fractures will fail first under shear and which may be the easiest to dilate. So that's what we're doing along the path of 16A to help choose zones where we're going to target that stimulation that's going to happen later this year. We actually did many stochastic DFN models. They've been built and evaluated and looked at the natural fracture population just to try to tease out some end member distributions for fractures to get kind of the mean behavior. So we have, the stochastic away from the wells, but essentially having deterministic fracture distributions along the path of the well itself. So I think I'm going to move on from here. I'm going to move on to the native state models. It's a continuum models and meshes. So, we're starting from the Earth model and also taking the information from the discrete fracture networks and move that into essentially our native state or continuum-based models for the site. All the data, and I've covered this before, but we've developed workflows that all the data can be transferred from the Earth model to the meshes. It's a pretty critical aspect here. So what you're seeing in this one, and the figure on the right, is looking at it. It is the inferred fracture porosity. So this is just essentially the top of the granite surface that you're seeing, the top 100 meters or so, somewhat damaged or weathered or essentially has a lot higher fracture density. So we're capturing that. And this is essentially directly upscaled from the DFN that I showed you in the previous slide. Also, associated subsurface properties, those are actually cell centers or nodes, depending on what they are, whether it's a primary or variable or a material property, come through into these models. The workflows are all pretty well established. What we end up usually sharing with the community is essentially just point data, CSV files with cell centers and cell node and nodal data, so people take the information as a scatter and build their own meshes or conceptualize their models the same way using the same data. I'm just going to move on. So we're actually in the process right now of creating new meshes. essentially with the trajectory of 16A, with all the drilling that we did, we wanted to make sure the toe of that well was further away from all the model boundaries. So we actually have reconceptualized the native state model mesh. It now actually, because of some of requests from the community, some people on this call, we actually took, previously we actually terminated the top of the model into the granite, and then just transferred conditions to the top of that for overburden, for hydraulic pressures via the earth model. What we're doing now, actually taking it to the land surface, is so we can do actually for strain measurement and to compare with strain measurements that'll be at the site. We actually have a larger domain with higher resolution at the land surface and the granite contact. I would say that this mesh is currently under development. It's not done. Our basic workflow, we use structure meshes, makes it easy to hand things off, but trying to get all this additional resolution, we were exploring some unstructured approaches to get essentially a triangulated surfaces and tets or hexes and a combination of the two. We do expect to have the revised native state models completed in the coming weeks. So we have all the data we need. The remeshing is taking a bit of time, of course, as always, but we should move that on here pretty quickly. Some of the other things that are going on with continuum-based models that I wanted to show. I'm not going to go into a whole lot of detail, but we are doing some heat extraction and some well design modeling, essentially coupling well hydraulics with the reservoir model. So using computational fluid dynamics and Navier-Stokes type equations for flow within the pipe. So we actually simulate the pipe, or the flow inside the pipe, the steel, the cement, and the structure around it, and couple that with the reservoir model, primarily looking at completion factors that can affect the production temperature. So we're looking at things like number of fractures or upscaled permeabilities, whether or discrete fractures. So we can take handoffs from either FracMan or from our stimulation models in X-Site from Itasca. Looking at perforation, so like a plug and perf, limited entry type scenarios. We can look at number of perforations, the perforation size, different wellbore diameters, different friction factors in the wellbore and such. We're getting pretty happy here, actually trying to work through ways to get, with the goal of having to have recommendations for the site design team for how these wells can be completed. We also look to the community, the people on this call, and some of our R&D performers to also help influence and guide information or add information to that discussion. Largely what you're seeing here in the center is essentially flow distribution for just hopefully that I mentioned. We'll be doing a 3 perforation or a 3 stimulations in the toe of 16A. This is in preparation for that. So looking at different 3 perforated zones, looking at the number of fractures, and actually looking at also the essentially the perforation diameters here and how that affects how the flow can be distributed between those different fracture zones. It becomes really important here. Now, with our goal is to have essentially as equal the fracture zone as possible, as it does affect our long-term flow and temperature production. Just shown here, just some very simple animations of that process and some cutaways here. Also doing some seismic wave and ground acceleration modeling, also to feed into some of just understanding the site as we plan forward here. I would say this is not for engineering design. This is coming from some of my colleagues, KT and Chendu at the INL, for seismic hazard work that they do. But essentially what we have is the same earth model and the same earth model domain. This is an early prototype of that, but essentially looking at velocity at the ground surface. And we're looking at this over a number of different stochastic type scenarios for displacements around those perforations, around those stimulation models for the toe of 16A. So it's just getting launched off, but we should be able to have some good information to share with the team as we go forward. Now, simulating the stimulations. Now I'm transitioning into primarily the work of Peng Zhujing at EGI and Branko and his team at Itasca. So there's a number of things we're trying to objective of most of that stimulation modeling is to design and optimize stimulation strategies so we can connect the injection and production wells. We did hold a stimulation working group meeting last month virtually, where when we reached out and presented some very preliminary models based on our old DFN and our old native state model. To parameterize the stimulation models. But what we're doing it for was to essentially have some ideas of some of the behavior we might expect. And as we stimulate 16A, and the end goal is to try to come up with essentially a base stimulation protocol, and then look at some variants of that. So when it comes time to do those stimulations, we have a pretty well-informed decision. Um, so in building up to that, I won't go through the table here that has some parameters on it, but building up to it, we did a whole bunch of pressure history matching for the injection testing in the pilot well in 5832. That's presented by earlier this year at the Stanford workshop, and also did some stimulations of the simulation of 16A in the toe with the current DFN, not the one that's updated. I just showed it's been done in the last few weeks. And we're actually right now launching a new round of 16A stimulation models. I would say that Branko, Pengju, and the team have a ARMA presentation that actually I shamelessly stole some of these next slides from. So our base stimulation model essentially is pumping at 20 barrels per minute for 15 minutes. We don't have any dilatancy in the fractures. The fractures are weak and a fluid velocity of 2 centipoise. And in doing that, so I'm showing some results here. This is things as I said, I shamelessly stole from Pengju and Branko, but looking at some of the fluid pressure in and around here, essentially you can see the outline of the DFNs that came from Alita's interpretations in FracMan and handed them into Excite, and look at different slip of fractures as well as open and dilation states. And just looking at some of the sensitivity type runs we're doing. I won't go into all these things, but looking at effects of fluid viscosity, and essentially how that can affect the shape of the stimulated volume. This is one case. There are a multitude of cases, and I would refer you to the ARMA presentation that's coming up here soon. And important, what it all comes down to is trying to come up with some reasonable stimulation indices. These are based from our old preliminary models, but we're trying to look for slip area, open area fractures, and stimulated volumes over a number of different cases of DFN. You can see some of the pumping rates, fracture dilation, stronger, weak DFNs in different fluid cases. So I won't go into these things, but the point of the matter is we're just trying to see which one of these will actually produce us the best stimulated volume and open area with the least amount of potential for induced seismicity. Now, this has been covered before, but all the data that we produce will and does make its way to the GDR. So a lot of things I've just presented today are hot off the presses or haven't even been fully internally reviewed, so they're not really suitable for external release. But be watching, and if you have questions or wanted this information, just shoot me an email or put a note in the chat and we can follow up. But as we get these things into the GDR, we'll make note of it here and on the forum as we go forward. So the standard acknowledgement slide, thanks to DOE for supporting all this work. We also have many of our stakeholders. I showed some of the work from Leapfrog Geothermal, our friends at Sequent, the state of Utah, the Beaver County, Utah Governor's Office, all been very, 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 very nice to the project, and we really thank all of our sponsors. I want to just give that acknowledgement before I went forward and started talking about the solicitations for the projects that were selected for award negotiation. So I went through a number of the topics and tried to pick out which ones I thought had a fair amount of modeling and simulation. Doesn't mean that they or may not think they do, but I actually reached out to the PIs from a number of these projects and asked if they wanted to provide an overview of what they intend to do and some of their goals. So the ones you see here highlighted provided me with a summary, a few summary slides of their projects. So I have 5 projects I'm going to talk about in more detail. If there are some of the PIs from these other projects that are on would like to talk about their things, if we get a question on it, we're more than happy. I'm more than happy to open up the floor later as we go. So first one here, topic 2, I'm going to give a little bit about the work proposed by Livermore National Lab and closing, well, I won't read the title here, but I'll just go to the slides as we go forward. So in topic 2, closing the loop between in-situ stress complexity and EGS fracture complexity. And I can't see my whole screen because of some of the notifications I'm getting from the the system. So the PI here is Peng-Cheng Fu, co-PI Andy Bunger at Pitt. Peng-Che is leading the modeling. And the reason I wanted to cover some of these is that I intend to, as we go forward and these projects actually begin, we will hold a monthly modeling working group meeting where we could talk with each other as a community. I mean, we do see FORGE as a community-driven effort. And so having the open communication between the team members as we all approach, similar goals, that being, making EGS something that we can actually rely on and be a commercial. So their main, some of the high level summary of this project is high fidelity modeling to interpret in situ stress from our experimental results at FORGE, then use those inferred stresses and calibrated model to predict stimulation responses. What's nice about this project is there's extensive validation using block size tests at Pitt. So, and I'm not going to go into detail. I actually do have some information on the key milestones and goals of each project. But I'm not going to read all these things, but I just want to show is that these projects all range over the next 3 years. In some cases, up to as many as 3 years. And we're going to work really hard to coordinate, make sure that if one team relies on another, that we can actually make sure that we're coordinated to the degree where we can essentially minimize duplication, but not avoid it. I think it's good to have multiple people doing the same thing with different approaches to look at some potential variability that we might see, but to make sure we're all well coordinated in what we do. So the next topic I'm going to go into is topic 3. Now, I believe I have, I did hear back from Rice University, Jonathan O. Franklin, whose modeling lead is Zamad Ghasemi at Oklahoma. They're fiber optic geophysical monitoring and reservoir evolution at the FORGE Milford site. And so they titled their project Fogmore at FORGE. And you could read it off there. People after my own heart with acronyms. So, essentially they intend to develop and deploy state-of-the-art monitoring solutions, just using distributed fiber optics, primarily DAS. As I mentioned earlier, we do have a number of wells that already have DAS in there, and we're working on making sure that we can meet the needs. We, as a FORGE team, can meet the needs for these other external performers here to have these things in here. They really want to improve the current microseismic based representations of fracture network, which becomes very, very important as we look for essentially not only reservoir creation, but reservoir evolution and reservoir operations. I'm not going to read all the text here, but their main point they want to drive home is they want to fuse all the data to generate a predictive model of the generated reservoir, which can guide our injection and production well drilling and optimize the resource. Something that we're already building to, as I showed some of the slides from the internal team. We're looking forward to working with this team to drive that further forward. Yeah, some of their key goals and is to essentially forward inverse modeling of the stimulation geomechanics using that fiber optic data sets as control, and also integrating multiphysics THM models based on finite elements and discontinuity methods. So or domain decomposition methods. It should be a good piece of work. Looking forward to work with this team as well. Topic 5 is the last topic here in the solicitation. And I did get 3 PIs provide me some information here. The first is Derek Ellsworth at Penn State. Their title or their project is Seismicity Permeability Relationships Probed via Nonlinear Acoustic Imaging. Looking forward to this as well. Experimental characterization project upscaled via modeling. So, I'm not going to go into all these things essentially, but they would upscale some of these acoustic indices to a reservoir scale as diagnostics for stimulation and management. And you can see that PFC-like models or tough react, tough FLAC at a reservoir scale, depending on what scale they're using. A number of co-PIs there, I won't read them all, but so once again, some of these key milestones is the micromechanical modeling at the laboratory scale and upscaled reservoir scale modeling at FORGE. So should be good to looking forward to this as well. This is in quarters here, but going in through essentially the first all 3 year for the next 3 years of FORGE. So next project here is the is a team led by Laura Pyrek-Nolte at Purdue, and they're looking at the role of fluid and temperature and fracture mechanics and a couple THMC processes for EGS. A lot of their project essentially is going to predict the interaction of fluid and temperature-driven fractures along with frictional interfaces. Looks really interesting. Ultimately impact long-term efficiency of the stimulation process in EGS systems. I won't go into the sub-goals here and such, but we're looking here. I lost a slide in there. I apologize. I think there was a second slide there, but I must have lost it, Laura. So I'll look a bit more here. But I think is looking at some of this mechanistic understanding of the frictional and deformational behavior of faults and fractures in EGS, and all the topic 5 has a good mix of experimental and modeling. That was kind of essentially the goal of this here. I would say the modeling team coming from or being led by Sandia and other people joining in between Sandia and a number of universities. So very good looking team here in this. I think the last summary that I got here was from the team at the USGS, David Lochner, Josh Terwin, Tamara Jepson, look at the evolution of permeability and strength recovery of shear fractures under hydrothermal conditions. They're looking to see how THMC processes, sorry, I've been talking too long, affect the stimulation and sustainability of fracture networks in EGS. That's the highest level of what they intend to do. But looking at building micromechanical models to follow temporal evolution of shear and static fractures, and actually been able to use these as to upscale and then put them into reservoir scale THMC work, if I'm not misstating here. A number of things here. This is also a longer term, looks like a 3-year project, but all this will fit in together well with the operational structure and goals for Forge. So I think that gets me to my, I see where my other slide went. So this, I'm sorry, is the second slide for the Purdue application. And I don't know how that happened, but I apologize. My slides somehow got blown up and out of order. But the Purdue team is looking largely, they're going to update Falcon, the simulator that we're using for the Forge work, for the continuum-based Forge work, and update it with a lot of additional, essentially finite element or hybrid finite element spectral boundary, approach for looking at some of the fracture movement, fracture deformation, and look at some different Galerkin schemes. Now I'm going to move on. I think I am. That gets me to the end of what I wanted to say. I'm going to look through for comments here to see if we have any questions, but I'm going to leave this slide up and do my best to do it. Okay, so I'm looking at the questions now. I'm not sure if you can see them on my screen. Question from Mike Dew. What geomechanical stress modeling software are? What fracturing design software use? Simulator. Basically, for the Forge Teams models, we are using a number of different codes for the stimulator or fracturing design software. So primarily, we're using Itasca's Excite code. That's being led by the people at Itasca, Branko Janik primarily, and his team, along with some folks at a number of different at EGI. I won't get into the details of the solution procedures. Just geomechanical stress modeling in general from native state, we are using the Falcon code. That is, that stands for fracturing and liquid convection. That is the code developed and designed at the INL for general porous media, multi-phase, multi-physics porous media. So it does THMC processes of essentially at different scales and different conditions. Hopefully that answers your question, Mike. If you want to follow up, please type in there. The next question here, very specific from Mike Dew against fracture geometries, rough length width. You know what? I would actually refer you to Pengju's ARMA talk, which is coming up, or you can review his Stanford paper, which goes into great detail on that. Or Branko, if I believe you're on, or Pikachu, if you're on, if you'd like to just kind of come off mute and help address that question for some of these things for fracture geometries. Are you on the call?
Yeah, this is Branko. Yeah, so basically, actually, I think Kalita would probably be best person to answer, but I can say that right now DFN is represented as a series of planar penny-shaped fractures with variable size and variable aperture.
Thanks, Branko. Actually, I misread the question, or I would have asked Alita. And Alita, you are on, so if you want to weigh in, Alita, please do as well.
Yeah, so I can address the geometry issue. So the natural fractures are representative. They are sort of six-sided polygons in the DFN just to represent sort of circular fractures. And the size distribution has been determined from nearby outcrop traces and also looking at sort of the penetration statistics from the FMI data that we have. So we have a pretty good power law distribution on the natural fracture sizes. I haven't done any work on fracture roughness, so that's something that I think our other modelers are introducing into the model there.
Thanks, Alita. And Mike, if you want to follow up, I'm not sure if that answered all your question, but we're happy to continue discussing here. We still have some time. So next question comes from Mark White. Do you have an estimate of drilling costs per foot in 16A 7832 well? I don't know what the final costs actually were. I know, and I don't want to speak out of turn here. If Joe Moore is on, I'll let him answer that. I know his schedule is very busy, so I don't want to assume that he's here, but I'll look and see. Joe, are you on?
He is not. This is Christopher. It's my understanding that the cost analysis has not yet been completed. So I don't think we have a number quite yet.
Okay. So Mark, I would say that, we put a lot of work into drilling that well, and we were trying to really design, and John McClellan did an extraordinary amount of work leading that team, looking to optimize the rate of penetration and not minimize costs. So this was essentially the first of a kind, trying some of these different bit runs, some of the different downhole mode motors. So we got really good rates of penetration, but that may not have equated to a gigantic cost savings. Mark, I see you came off mute. So you want to follow up with your question?
Oh, no, I just wanted to say thanks for trying to respond to that. And I'll follow up, and I'll try and get the information from what was it, Christopher, that chimed in there?
Yeah, Christopher Teese is our communications lead.
Oh, okay. But would he be the best contact, or
Joe or John would probably, Joe Moore would probably be your best contact. Anytime you're talking money, it's Joe Moore.
Okay, exactly. I'll do that. Thank you.
All right. No, thank you, my friend. Jonathan O. Franklin. So it says, which code is being used for the 3 wave field simulations shown for strong motion? I'd like to leverage, refine the model for our experimental design work. So Jonathan, that actually is a code called Mastodon. It actually is an INL written code developed on the same modeling simulation framework as Falcon. So, Falcon is our geothermal reservoir simulator. Mastodon, is essentially does strong motion and essentially velocity models. And it was written for site hazard analysis for nuclear facilities. So that's where it is like an NQA level 1 code. It is open source. So I'll follow up with you to send you a link to the Git repository for it so you can pull it yourself. And we are working, essentially to have essentially, so the beauty of I would say the beauty of some of the code design that we're, if we're using a lot of codes under the same framework, is that they all, essentially run on the same solver, and they can even run on the same meshes, but we could have direct handoffs to from the reservoir simulation code, Falcon. So if we do want to simulate a slip or a seismic event, we can actually generate with that the location, the hypocenter, and the amount of energy and whatever essentially directional plane that moved, and hand that off to that wave field propagator Mastodon, and essentially kind of couple those two without having to bear the burden and the overhead of trying to solve on the type of mesh it takes for those kind of calculations, because they're extremely fine meshes. So hopefully that answers your question, and we'll get that out to you. that gets to the end of my questions, or the end of the questions that were posted here. I see Julia just posted a link. I'm not sure what that link is for, but any other questions? I'm glad to take them. Also, thank you, Julia, for Mastodon, and I'll send out the. There is a Git repo. Oh, there you go. Thank you. All right, you got it. You could also find links there for a number of the other codes that we use. We'll have a lot, a robust selection of FORGE forum talks here coming up over the next few months, because there's so much modeling work that's going on. So what I wanted to put out to the community is, if you have a request for a forum talk for something that we're doing, or even something that we're not doing that you think we should be doing, whatever, don't hesitate to send me an email, and I'll type my my email address in here right now. And it's just shoot me a request, and we'll see if we can get something scheduled. But we do, coming up in the near future, I do intend to see another stimulation modeling forum. We'll probably see one on DFN. We'll see one on the details of the native state models. We'll see detailed presentations for some of the seismic wave propagation modeling, and then as we get deeper into some of those external awards, once they're done with negotiations, we'll likely start having some of those teams present their plans and their work in greater detail than the crude overview that I just presented for them. So if there's nothing else, I think we can close for today, but I'll stay on if anyone wants to just chat and ask questions. So I thank everyone for their attention today, and I'm looking forward to future forums and future work. Thank you. Oh, question. Okay. Mike's asking a question that may I have some understanding of the in-situ fractures. Are they mostly open, sealed, partially, average in-situ fracture sizes? Alida, will you answer that question?
Yeah, so let's see. It's kind of interesting because most of our information about whether these fractions are open or closed or sealed is coming from the FMI interpretation. And, the FMI interpretations are saying that a lot of these fractures that the wells are intersecting are open. However, when we do the well testing and we look at the, the permeability of this rock, it's very tight. So we're getting this bit of a mismatch between the FMI, which is showing potentially open fractures as far as if you just look at the resistivity contrast between the fracture and the matrix. And when you actually test the well and you try to inject some fluid into there, you're not, the rock's not taking it. So while these fractures look open in the FMI, clearly they're not very conductive for whatever reason. And I don't think we have the definitive answer on that. So what we're doing is when we build the discrete fracture network model, we put in all the fractures as represented by the population we're seeing in the FMI. So whether they're open or closed, we put the geometries in the model as pre-existing fractures. And then we're adjusting the permeability of those fractures to match the well test results. So we're making them not very permeable, not very conductive, not particularly open, but they're present. So under stimulation, there's that discontinuity there that would be more likely to fail than, say, intact rock. So it's a bit of an open question.
Thanks, Alida. So following a little bit, the well testing permeability comes in about 10 to the negative 18, 10 to the negative 17 meters squared. Fracture processes are exceedingly low based on the well testing. And I'm not sure what the exact number is, but well under 1%, if I'm not mistaken, Alida.
Yeah, I'm sorry. I
Yeah,
don't
that's
remember
fine.
that. I don't
I don't
remember
want to put you on the
that
spot. That's fine.
offhand.
Pengju, I see you came off of mute. Did you have something you wanted to say? Or Pencheng, you came off
Oh,
mute?
okay, it's me. Yeah. Thank
Oh,
you,
sorry.
Rob. So I was looking at the histogram, right? So apparently most of the fractures are within between 1 and the 0.5 millimeter. Your statement was says 0.1 millimeter range. I guess what you mean is they're a fraction of a millimeter. They're not really in 0.1 millimeter, right? They're larger than 0.1 millimeter. But I look at the log says the log was only on the segment of 137 feet. There are about 15-ish fractures with aperture larger than 1 millimeter. So even for the large fractures, the density is 1 every 10 feet. For a system like this, I'm just wondering if actually in the end the performance or the behavior is going to be dominated by these larger fractures. They're actually not too scarce, right? There's every 10 or so feet, you get one of those. Is that the fair assessment?
No, well, I would say that's the issue that we've been struggling with is, you will see some of these. So that's what you see here is the mechanical aperture. That's what comes right from the FMI log. That's what it returns. The issue is that none of the well testing data doesn't match. So having a fracture that's that large and also the drilling data, there's essentially no fluid losses during well drilling. So we didn't really encounter any zones where fluid was lost. So we were getting, a fracture with a 4.5 millimeter aperture every 10 feet. We'd be losing a ton of fluid, and we didn't lose any. So,
okay.
So it's I wouldn't say troubling, but it is something that we kind of work through. And we did some of our earliest models. How we discovered that is we tried actually doing history matching from some of our injection tests based on the apertures that were returned from the FMI logs, and it just simply could not come close to even matching the injection data because with having something that's that large in the 4 millimeter range, you really don't need much of a pressure gradient to push fluid in the reservoir. So we ended up scaling those mechanical apertures down by 2 or 3 orders of magnitude, maybe even 4, in the history matching models for the injection test to even come close to getting a match.
Okay, yeah, thank you. My second question is you have like a 17 or 18 proposals. And I understand most people don't like others to look at their proposals, but they do each have a public outline or abstract kind of, one pager. So when will we have a chance to look at all those so that we can identify, collaboration opportunities?
So that falls right in the middle of not my department. So I can't, I'm not, I can't authorize, you know what I mean? So that is something I think the best answer to that is likely if award negotiations when they're successfully completed, those things will be released. But until then, those things are still in negotiation. I wouldn't say they weren't selected for award; they were selected for award negotiation, if that makes sense. And so until those negotiations are complete, I would bet that, and I'm speaking for Shirley Streff, the contracting officer here. So I am not the definitive, and I don't have the authority to make any of those decisions. But that is what I would assume would be her interpretation or her response. But I would say that we do intend to have strong collaborative efforts. So when these things launch off, that's why I was asking, some of those projects for the summaries. And even, I listed about maybe half the projects that were selected for negotiation as having a significant modeling simulation activity. There may be, I wasn't trying to be inclusive, but I didn't want to read into anybody's what they intend to do or try to interpret them 100%. That's why I asked for the performers to provide that information back to me. So I didn't want to get out ahead of the headlights because, I'm not involved in all negotiation. I'm involved in a little bit of it, but so I'm not sure where the status of all those things are, if you understand my meaning.
Yeah, of course. Yeah, thank you.
Okay, well, my pleasure. Anyone else? You can just come off mute if you like. And I could talk about this all day long.
Yeah, this is Jonathan. Just going back to the seismic simulations, do you guys, for your native state model, do you have elastic properties nicely populated for all of those, for the whole geovolumes, or is it just kind of, the contrast between the alluvium and the granitoid body at depth?
It is just bulk elastic parameters between granite and sediment.
Gotcha. Well,
Yeah,
we'll
I
work on refining that
like,
a little bit. Hopefully it'll
I
be
would
useful.
love to have it. So having like a detailed petrophysical analysis of all the well logs we have in the area, because we do have a lot of VSVP or seismic velocity logs in some of those wells. I think there's a whole wealth of information you could take from some of the existing logs and tie that in, and that's why we essentially was using the structured mesh so we could make easy statistical distributions, just move them back and forth. So I'd welcome that kind of information. Thanks, Jonathan. Other questions?
Yeah, this is Hong Kyo-yun from Sandia. I have one technical question. So when you have some kind of meetings last month, you mentioned, so we are allowed to creating some kind of project account, HPC account at Idaho National Lab, and when those efforts can be initiated and how easily actually we can do.
Once your contracts are awarded and negotiations are finished, I'll be happy to help you.
Okay. Thanks.
And we could talk offline in greater detail if you like.
Yeah, some later on, I think.
Okay, perfect.
Yep.
Thank you. Thank you. I'll even take snide remarks before you go if anyone wants to throw something out there. All right, everyone. Thank you for your time today. I really appreciate it. I think it was a great meeting. We're looking forward to work with you, and we'll talk soon. Bye now.